Okay. So, these have to see everyone.
Bring them for him.
Heroes, animation, instruction 6. Okay. So, we're going to be discussing today, we're going to be discussing current and resistance today. So, who can remind me something about, anything we can remember about current? So,
The inverse
what
charge.
is current?
Flow.
Flow of what?
Electricity.
Electricity, which is made up of?
Electrons.
Charged particles.
particles.
There we go, charged particles.
And they go in a general direction.
So, what type of charged particles do we have?
Electrons.
Raise your hands, guys. Jake?
Protons, electrons.
Protons, electrons. Okay. Okay.
And if you were wondering, it's measured in coulombs.
Right. Very good.
Or cool lambs.
Okay. It's coulombs. What else to remember? What about more things? Just about. I want you to remember current.
Positive and negative. Charge flows one way and the current flows the other.
Right. The charge goes one way. The current goes the other. That's very good. You have to remember that. Okay. Now, the reason for that, and I don't know if I hit that with you guys, so I'm just going to talk about this right now. So let's say we have the charged particles, okay? We're going to say these are negatives, okay? And they're flowing this way. So, Andrew, what were you talking about? What did you have just said?
So,
Which way would be current? How about that?
current would be less. Towards,
Right.
towards the minus, which is going to be in.
Okay. There's a reason for that. And the reason is, so basically, the way we manipulate, okay, so the biggest thing is we know that electricity flows. The problem is we have to, or originally with electricity is, we had to manipulate it to control it, to make it useful, all right? So the way we manipulate it is, what do we know about electrons?
Does that have to do with the
Oh,
fact
negative. Oh,
They
wait,
attract
one
a
second. Raise your
positive
hand.
charge.
Say negative. What did you say, Gabe?
They're attracted to positive charge.
They're attracted to positive. Very good. So they're attracted to positive charge. So that's why if I put the positive here, that makes sense. It's going to go in this direction, right?
Yep.
Right? So what should be at this end?
negative?
Right. So let's say this is a battery. We
Like
connect this
charges
all
right now.
with a battery. The charges go from the negative end to the positive end. That makes sense. Current, the way we denoted it from the time of Benjamin Franklin, was he decided before he knew about the charged particles, was, I think current's going to flow from the positive end to the negative end. So we based everything of science, of everything we know about electricity, on current flowing from positive to negative. Guess what? He was wrong.
Ben Franklin was a smart
Yes. But even smart guys make mistakes. And in this case, his mistake was he made an educated guess that everything was being flowing this way with the current. It wasn't true. Okay? So we now just remember that current flows in one direction and the electricity, the electrons, are moving the other direction. Okay? Now, to have a complete working and operational circuit, what you need is a continuous flow. So take, for example, a lamp, lights, okay? You take a desk lamp. A desk lamp is plugged in, right? And you can turn it off. So if I drew a desk lamp, we'll draw it over here. If I draw a desk lamp over here, and I'll just erase this part. Actually, no, I'll put the light bulb in. I'll make it see through desk lamp. Okay, if I have a desk lamp here, and I have a cable coming from an outlet, okay? We'll say the outlet is over here. In what direction is the current flowing? If I were just to throw this out, this question.
Towards the lamp.
No, away from the lamp.
Why not both?
Well, there are two lines. Because you've
Well,
got
hold on.
The electrons are falling to the lamp, but the current is flowing.
no, but when you plug in a lamp, you've got one that's a negative and one's a positive.
Right. Okay,
One
so
of the prongs.
yes, these prongs represent a positive and a negative. So the thing is, we just said, to have current flow, you need a connection. So they have to continuously flow. They flow, right? So in this case, if it's on the same
Got one
line,
sticking up.
you have one coming up, going up, coming up, coming over, coming down, and back. So current flows in both directions in this case.
Wait, what? So what is? How is energy used then? Like what? It just goes back in.
Just goes back in. Just goes back in.
So,
Because you have to complete a circuit.
but like energy
Why
is
is there-
lost when you do that, right?
I told you I needed to record this. Nick, please.
Sorry.
Okay.
Energy is lost when you do that, right?
Energy is lost. Why is energy lost, Poe?
Because you have to.
These are wires.
Or else you never run out of energy, so it has to be lost, right?
But why? What's going on? Why do we lose
you have
energy?
to excite
Don't the electrons flow off to like the side? Just sort of like.
Well, think like this.
Like this
Do we
wires
lose?
and hold it in.
Hold on. Nick, going along that case, when we hit the sides here, right?
Then it bounces, but
There are those
not all the
like
time, right?
outtake tubes or something like that.
Yes. But I'm just trying to say, when we hit the sides, do we lose energy? Makes sense. We do. Now we're not in an ideal world. This is basically where energy, like we're saying, energy is conserved, but energy is also used because we have something, a mass, moving a distance. So let's say an electron here starts over at the bottom. We're going to be moving it. So mass times distance
Equals velocity.
equals velocity.
No, it doesn't.
Good try. We have the mass. Think about it. What is equal to work? What is equal to energy?
Work is
W
force
equals
over
MD.
time.
Work
Energy over time.
equal to force times distance. So it requires a force to move this electron over a given distance. So do we have energy being used?
Yes.
Right. But then what can gauge how much energy is being used? Any ideas?
The
How
efficiency of the light
strong
bulb.
the
The efficiency? Okay, that's a good
How
idea.
we write
How bright? That's how much. That's how intense. How much energy is getting into it.
Yeah.
Okay, that's a measurement of it. But what affects how much energy is being
the
used?
distance it travels. Well,
Oh,
no,
Right, right. The distance it travels. The more distance you have, the more energy you need. Makes sense. So, let's say wire, for instance, this one. Okay, the one I'm holding here. This wire here has a length. I'm just going to draw it as this. Okay, as a tube. So we just stated that, or Chase just mentioned, that the length of the tube is going to affect how much energy is being used, because the more length it has, the more energy it's going to need to travel that far. That makes sense. Okay, what else? Do we have any other ideas?
The width of the cable.
Why? Why the width of the cable?
Because if it's wider, they pass slower and there's more of them.
Well, think about this. Think about traffic. Think about traffic. Cars.
More can fit through.
Yeah, more can get through if it's wider.
Right.
Less collisions. Fewer collisions, I should say. So, cross-sectional area. So I'll do it as
Not
this.
the type of wire you use.
That goes as well. But we'll get into that in a moment. Remember that. So the cross-sectional area, the larger it is, so as the cross-sectional area goes up, energy usage goes
Yeah.
right.
Because there's more particles.
Energy usage goes down because you don't require as much energy to pass through it. Okay? So now Fears just mentioned what? Type of wire. Type of wire, yes. Why would that matter?
Some of them more conductive than others.
Right, some of them are more conductive. Allow electrons to pass easily or more easily through it. So we have length, cross-sectional area, and then type of wire, material. By the way, if you're not taking notes, I suggest you should. Because these are the three types of resistance.
What?
This is all resistance.
What are the three types of resistance?
Your length of the wire, your cross-sectional area, and the type of material. Your three types of resistance. Okay? So resistors, as we refer to them. Okay?
You say that one more time, please.
Well, it's on the board. Here. Okay? So resistance is
Length of
the
wire.
amount here, some sort of quantity, the amount of resistance electricity faces while going through a given place. Okay? So, let's say we can measure that. Now, earlier when I showed this, right? Positive, negative, right? What does this mean when I'm talking about positive, negative? Think about other terms we were talking about.
When there's an extra electron.
Okay, we've talked about two different terms, current and voltage. What does voltage mean? Who remembers the definition?
It's the potential energy.
Potential energy over coulombs.
Potential, okay, that's the relationship. So that's the potential energy over coulombs. The potential energy to do what? Anyone?
Like for a charge? Isn't it like
Yeah, for a charge to do what?
To light something. Or
Basically to move. To give energy to an electron. So here is your electric potential to move the electron over to have current. You have current going through this area, and you have your electric potential at the end of the area. That's connecting. That's your battery. That's what you mean when you say 12-volt batteries. They have an electric potential to push electrons to their given point. Yes.
Do you mind restating the types of resistance? I got length of wire, type of material.
And the cross-sectional area. Okay. Now, if there's anything you miss on this, there's also something you can do some reading on the textbook. I posted those pages online. I'm also going to be posting. There's a very nice little chart that talks about different types of resistances and how they affect each other, causing rate to increase in current and voltage. Okay. But there is a relationship. There is a relationship.
Cross-sectional
Sectional area.
So, if we know that, as Connor should put, voltage is the electric potential, which is potential energy, right? So, electric potential, if we increase the voltage, what does that mean for a current? Does it increase? Let's say everything else remains the same. This stays the same. If we increase the amount of energy in here, what about current? What happens to current? Any ideas?
I feel like you said think of traffic.
Yeah,
Is that,
If you increase the voltage, they go faster.
they go faster, right? Which does?
More
They're getting
like the distance
to the point.
can be longer.
No.
Less
Think
energy.
about current. What's happening to current?
It's faster.
Increasing.
Higher.
Right, because what is current? What is the definition of current?
Charge over second.
Yes, the rate of how many charges are moving over through a given distance per second. So we can now we just discovered, or basically said, that voltage and current are directly proportional. So I'm gonna draw it like this. I'm gonna write it out like this: voltage divided by current. I'm writing that out because we know when any two type of constants or variables are divided, they're directly proportional. If the other, whatever it's equal to, is constant. Right? Does everyone remember that? Let's say it was equal to 1. If I increase the top by 2, what do I have to do to the bottom?
Increase.
So, yeah, right. I have to multiply the bottom by 2 as well. Very good. So, I'm going to let you know what this all is equal to. Anyone have any guesses?
What is what equal to?
What is V over I equal to?
V over I
That's voltage over
is voltage over change in
Potential energy.
Good try. It's resistance.
I was gonna say amps.
R equals V over I. So the resistance of, let's say, a wire
what
is equal to the voltage of the battery divided by the current flowing through that wire.
Why is current high?
I forget the reason why. I believe it's a Latin thing.
Wait, R is resistance.
R is resistance. R stands for resistance. It is measured in its own unit, though. Okay, it has a fancy way of writing the unit out. Okay, so I need you to pay attention. Okay, so it's measured in ohms. Okay, ohms. Okay, that's how you spell it. It's measured in ohms, and it's referring to R here. Okay, so it's measured in ohms. The way we denote that, if I were to say it was 12 ohms, so let's say I have a circuit. I have 12-volt battery, all right, and I have current that is 1 amp. So 12-volt battery with 1 amp current. 12-volt battery, 1
Current's measured in
amp. Yes. All right, you weren't here yesterday. Okay, 12-volt battery measured divided by 1 amp. So how many ohms do I have? What? 12 ohms, right? So pay attention to how I write this. That is an ohm.
Whoa. What? It looks like a mountain.
It's an omega.
It actually looks like a cactus.
Giving the middle finger.
It doesn't look
Omega's like the thing with the.
Yeah. I'm saying if I'm drawing it quickly, that's how I would do it.
I would not draw quickly.
Am I not? The reason why I'm showing you that is because I'm most likely going to draw it quickly in the future, and you guys have to understand that's all I'm referring to. Okay? So if I was going to read
symbol online.
Here.
It's called an omega.
Oh, like an anchor.
Like the water.
Proportion kind of thing.
So basically, it's if you want to say it's an M with a large hump, okay? But that's what this is what an omega is, okay? So when we denote, when I'm having, let's say, word problems with this, or I'm writing this on the board, this is what I'm referring to. When I have this symbol or a variation of it, that is referring to ohms, resistance, okay? So why does this matter for you guys? I don't know.
We use light in every single way.
What you get defensive? Okay. The reason for I'm telling you guys is because you can actually, after knowing this stuff, you guys can actually test your. Let's say if there's something goes out in your home, you guys can fix your own stuff.
Oh, I wouldn't suggest we do that. I'll end up electrocuting myself.
Okay. As long as you
I am
have
not very good.
the right
but
insulation
you know.
gloves. So the reason why I have my fencing stuff today is because I mentioned to you already that fencing, the way it was started, was basically for dueling, but as people wanted to start and basically duel the same people more, and have more fun with it, they made it into a sport. Yes, less dying. But the thing is, when they made the dull blades, and they were still fighting, it was very hard to tell when you're moving around the blade and you have no idea who hit first. You have like 8 different referees going, I think he hit first. I think he did that. So I forget who was the person who came up with this, but basically it was decided, you know what, let's have science help. So here they have a body cord, this is what it's called, a body cord which basically has 3 individual wires connected to each one of these prongs. Okay? They connect to each one of these prongs and run a current through. The current runs through all the way through your coat, down your arm, out the back, and if I can find my wire, where is it?
It's in between your legs on the lower end.
I know, I'm trying to get it from the top. Oh, there it is. Okay. So this, I'm going to let you know, in our world, this is instantaneous. Whatever happens here goes straight to here immediately. That's like the flick of the switch. Flick it off, it doesn't take time to turn off. Right, you're completing the circuit. Because you have to have a completion to have your electric potential working. Okay? There must be a complete circuit. So, now in fencing, there's 3 different types. There's 3 different types of fencing. Fencing blades and fencing subsports. It's like saying karate, taekwondo, and all those. Okay? Yeah. So this would be a foil. And a foil, if you notice, has a 2-prong connector. That doesn't fit this.
Can only hit people in like that area.
Yeah, I'll be talking about how the target area works. But basically, this has current running. This actually has a current running through the whole time. If you look at this, see this coating? This, basically, it's insulation. It's insulation, so you don't get shocked. Because this is all charged when plugged in. This all have electricity. It all has current running through.
So you get shocked if you touch the metal piece?
No, only if you had, like, let's say, wet hands. Okay. You guys okay over there?
Yeah. No, he's talking about my symbol for the omega.
Okay. Alright, so it's not.
Yeah.
I've gotten shocked several times because when I was fencing in high school, basically I didn't like the grip of an insulated grip. It didn't feel good, so I used a grounded. This one actually, in fact, and basically this was all metal and non-protected metal. So the charge goes through And once you have sweaty hands, as soon as the light comes off, you have to shut. Now my teammates figured this out, proceeded to prank me with this, and now it's conveniently electrical taped because that is an insulator. It stops the charge.
Why can't you wear gloves?
Looks like it's in pretty good shape.
Yeah, why don't you wear
Yeah,
gloves?
just like that.
I do.
So that doesn't do anything.
Why don't you just wear
It's supposed to. It's just depending on how long.
Why do you wear like the doctor's gloves, the latex ones?
Because
Rubber gloves.
once you get stabbed in the hands once, it's broken.
You get stabbed in the hand?
These
Yes.
Ouch. That's mean.
Okay.
Why don't you wear
So-
a latex glove and then put that glove over it?
Gloves on gloves on gloves.
Yeah, I
That's
decided.
what we use for lacrosse when it's cold out.
Oh, really?
Are we taking you on this? Are we gonna fence
We were pogies at Ryan.
Pogies.
Like little mittens.
Not
I
bad.
got my pogies.
I think we're calling Mr. T.
Okay. So I'm going to show you what this looks like.
Wait, Mr. Easy, did you fence for the U.S. Olympic team?
Not the Olympic team.
Like the national.
Mr. D, I know a kid in Italy who's the number 1 under 16 or under 18
Y16, yeah.
fencer in Europe or something like that.
Is he good?
Is he good? I've never seen him fence, but he's number 1,
So-
so I figured he would
I
be.
can beat him.
You could be him.
He's a
All
guy.
right,
It's
so
really
some out.
Rust.
Overhand.
So there's 3 types. I just showed you the foil. Okay.
Is there such thing as
This-
slash
Yes.
in fencing?
This one is known as the FA. Okay. This is
It's
the one I
rainbow.
primarily
It's
do.
rainbow.
Oh, I primarily do. I used to do foil much more when I was younger.
What's the red, white, and blue one?
Okay.
That's gonna be.
Do you still fence?
You got us.
Alright.
Okay. But I'm trying to get through everything because it's a tight spot to fill in everything. Okay. So basically, actually, it should be on. So what happens is, in this case, this one's not charged the whole way. I prefer not on my hand.
Say
No.
no for his.
Okay. So in this case, you have a wire going down the blade. This one's not charged, and therefore doesn't need this part. The only thing that's charged is the wire running across down the whole blade. I believe I showed you guys this yesterday, that there's wires that run down the whole blade. That carries the charge. So what happens is, so can anyone tell me why it only goes off when I hit? Right, what happens when I press the button to the top? Right, it's like a switch. It's just like a light. It turns on and off. So here, I push it down, and it'll keep going off. Okay?
Yeah, it's like a little.
So we're going to cardiac arrest.
Yeah, I barely hear it now. It's been a while. Okay, so that is for Epic. Okay? It doesn't. All it requires is just a circuit to complete. Okay?
Yeah, it's like something flatline.
Now, there's a third type.
And those are just medical trials where it's like, I might
There's a
be
third
really-
type,
and then they just get out.
which is Saber.
I want to do that one.
This is Saber.
Sweet.
That's cool.
Why does it have a GFA thing on it?
That's what they wanted for when the club wasn't. You're not supposed to. Okay, so basically, with this one here, this one is charged same way as the other one, right?
What are the one?
So that's a foil. Okay, the foil had one wire going up the blade, and then the rest of it was charged down here. This one is the exact opposite. The only thing that's charged, okay. The only thing that's actually, this whole thing here is charged. This whole blade, okay. The grip here protects it though. So, in foil, in Saber, all that needs to be touched for a target to basically consider a win is just a touch. You can touch on the body, you can touch anywhere, doesn't matter.
What about the other
So
sword?
how do they send
Other sword doesn't count.
It's not plugged
It
in.
doesn't complete the circuit.
Oh.
It's not going off because I don't have the body cord for it. I have one here that is for this body cord, but it's broken. And I'm going to show you guys why it's broken in a moment. But here, this one, this is your defense. Because you can get hit, you can basically, your allowed target area for Saber is from the waist all the way up, including arm, and basically the whole torso.
Head?
Yeah, head to
hit you in the face?
Yes, the head. So basically, in this one, because the blade's charged,
They hit you.
as soon as it makes contact, as soon, not pressure, as soon as the electrons have a chance to jump off, the thing goes off. Yes.
Are you
So-
sure you're like,
So like here, put it on your
you
arm.
poke it right next to it?
That's a touch. It's like so that's
Well, what if you get
Are we
close
fencing
enough?
usually? Are we gonna fence?
What
I'll
if
let
you
you guys
get
hold
close
this.
enough that
Oh,
you're
I'm
not
not fencing.
touching?
If we have enough time, I'll allow you to put on a mask and you're allowed to fence me. But you're not allowed to fence each other.
Can I fence you, please?
I want to fence you.
Now,
I don't need
not yet.
to sword.
In my
I'm
skirt.
So
Be playing that.
the thing with this, now this is a foil. Okay. The thing with the foil is you're only allowed to hit in this area. They wear a metal vest. Think about that, a metal vest that they connect with a ground. Okay, they connect it, charge up the vest, basically having electrons flowing through the vest, and this hits. Okay, this clicks as well, but it only goes off correctly if it is touching metal. If it touches a place that's not not grounded, that means what happens is it sends off a different light. Actually, that's why you have two different lights.
So if you
White
started
one.
whacking that thing, then it would go off, right?
Yes. Basically, in foil, you're only allowed to hit here, the torso, and not the arm, and you're allowed to hit the neck. And
You have to poke that. You can't slash that.
no slashing in this one. As here,
Saber.
you'll see here, look. See this? This mask? This has this metal covering over it. The metal covering means that you can hit it, and it's a target.
Could you theoretically poke the neck on the thing?
I've done that once. And
Because I
That would hurt.
no, there was one famous incident where an Olympic fencer died because he was fencing a beginner and the blade broke. The blade broke sharp, and the beginner held his arm out, and the blade punctured through the guy's skull.
Ow.
That's
What do you mean he held his arm out?
He basically, the guy was coming towards him, and he goes, "Eh." So that's all he did.
Oh.
This is like a bare blade. This is just metal.
You didn't realize the blade
This
was
is
broken?
just metal. This is what a blade is. Okay? It happens so quickly. Like here's one of mine.
What's the coolest type of fencing out of the three if you had to choose?
Saber.
I don't want to. Okay, so this is a blade that I broke. As you can see, the reason why this doesn't work, other than the metal broken, is that the wire got disconnected. Here, if you take a look at the wire got disconnected. So this part could work if you charge this, if you connected this part here, but the rest of it won't.
Should have dagger fencing.
They do, but it's not Olympic. Okay, so here,
Ninja style.
basically, you can also know it breaks flat. This is actually what happened after that incident with the Olympic fencer dying. They decided to basically design all their blades to make sure they break flat. So
Did they do that
therefore,
with safety glass?
So you get
How
stabbed.
big?
and, like,
there's
so
like
the blood dog.
I don't know, it's like one so, I don't know, I could probably mine broke quality of the blade. I think it break about 3 a year. Probably.
How much are
Too
they?
hard in the paint. You just went too hard in the paint.
So-
How much is the saber?
Wait, isn't that like safety glass, Mr.
Depends.
D? Where like they make it so if you break it, it breaks a certain way.
Yeah, that's what I'm saying. It breaks flat.
What would a mid-range saber call?
Mid-range saber. If you want to probably buy low end, a practice one that's not electric, you probably get one for 20.
What about electric?
Electric, at least 40.
What's your most expensive sword? Such a difference.
10,000.
No, I want to know like how much.
This one, I built myself. If I were to buy it straight out,
Did you do the whole?
180.
Color the blade yourself?
Yeah. What?
How did you color the blade?
Oh, they dip it in coating themselves. Now, I'm gonna have you guys. I want you guys to come over. Come up.
I want to spend.
Hold on, not yet. We still have 20 minutes for it. I have to show you one more thing before we do that. Okay.
Put me on this camera, my skirt.
Captain America.
Hold on. So, the thing, I have this here. This is a multimeter. Okay? So I'm going to show you, I have it currently on one setting. The setting is called, please don't mind. Wait for the okay? So, here, the multimeter has different settings. The different settings here on the current one is on basically to say if it is a continuous circuit. reason why they're sharp also is because so you can get into really small places. It's like circle. So here, this one is a body cord. It's the same one I'm wearing. So if I hold this, and I want to hold this one.
Yes.
Hold this one.
Yes.
Okay. So if you take a look at it, the FA is actually really basic in the fact of what they want to do with the electrical circuit. So hold it there. So now what that means is that there are continuous circuits being done. So what does that mean? If I touch them all together and I test them away and I put them all together, they all worked. What does that mean? Right. Each individual wire here has no breaks in it. Okay? So let's take this one. This is a foil body plate. We're gonna see if it has the same thing. So can you guys, when you hold
You can tell it's gonna be different.
well, it doesn't mean one. So I need to touch the problems. Okay? So that's connecting. That's connecting. So this one works. The 3 wires are connected all the way through without any breaks. That's all that's basically was saying, is that this worked. Now you'll hear it was actually going off just now because like this. That means like full connection. Okay? So let's see, what else do I want to test? Give me that one. Now, here, this is the same one. This is very similar to the one I just had. Hold it, please. Okay, so now if I'm going to try the same thing again. That's going. Goes. Now, try wiggling it. Okay. Wiggle it from here and keep this. Oh, it's going to break it. Ready? No, so hold it. I need you to hold the top part. So I need you to wiggle here and wiggle this part. Okay? Yes, you need 2 minutes for this. Keep that stick. Keep it sitting. So that one, even through the stress of moving it around, is still connected. This one as well. So let's see if the ground still works.
Not as well.
Right. That's a loose connection. So that what that means is the circuit's only there half the time. So now I actually have a broken blade here. Okay. Let me see. A blade that won't work, I should say. So if I look through, okay. If I look at this one, I'm going to let you know there's a broken connection.